Okay. Questions? Okay, let's start with what we have done yesterday. I prepared a little revised version of the notebook concerning the computation director law. I realized that to use the strategy we used yesterday, I would spend too much time explaining what pandas really does. So I should talk you about indexing of data frame, illustrating some features of the method that pandas has in order to manipulate data frames. So I decided to switch to another method that use pandas to read in data from files stored on the disk. But then, as soon as the data are loaded, and I will convert everything in Numpy array, so we will work uniquely with the Numpy arrays that we know better at this point of the course. So this is a new notebook. This is it's not still loaded on the GitHub site, but you will do during the day. So you will have to well, a material that you can use in the future. Richter Lovney's example NumPy polyfit revised version. So I start by loading the same libraries as I did yesterday. So I load pandas, NumPy, and matplotlib pyplot as PLT, PDNP PLT will be our alias. So I run this cell. I use pandas method readCSV to read data from from a file, which has this name here, just as we did yesterday. We use the Catania describe method to see what is the content of the file. We see the first lines, first 5 records in the file by using Catania heads here. Then we are interested in looking at the magnitude. So we select the magnitude, the column of the containing the magnitude value of the earthquakes, and I make an histogram with 20 beings, 20 channels. So I run this line here. So we have our data here. Then I transform everything to the NumPy array. So I define an array here by using the function toNumPy, which is a pandas function that takes a data series. So I already selected the magnitude columns in the data frame. What I created here is a pandas series object, so a list of values under the heading magnitude. So this is just a sequence of numbers. And I convert the sequence of numbers, this series, this pandas series, to a NumPy array by using this method, which belongs to the pandas library. Okay, now we have our NumPy array, and we containing all the earthquakes with all of the possible magnitudes. And we want to select only the events at having a magnitude comprised between 2 and 3.5. Why 2 and 3.5? Maybe I can discuss it later. So I write this parameter here. There's just 2 variables, min mag and max mag, which are the limit of the interval that I want to select. Then I select the event in this array here by using this function, NumPy function, where that we already saw this function in one of the first lectures. So where accept a Boolean in a Boolean expression in the as argument. So you will look at all the case, all the position in this array for which the value Catania, Mag, and P, this array here, are values which are greater than min mag, so greater than 2, and less than 3.5. So I have this function that will identify the position of all the element having magnitude which are in this interval and store the results in an array which is called cases. They are just an array containing position of the element having these features. Then I use these arrays to select the events in the Catania, Mag, and P arrays, and I will produce this new array with all the events having the magnitude in between these two two values. So I run this cell. If one wants to see the positions which are stored in cases, you have this array, which is a very long array, contains a number of positions which are integer numbers. So then I go to see, for instance, the Catania, Mag, and P lim, and I see some part of the array. You see that every number that appears inside this array is as a value which is not lower than 2 and does not exceed eventually 3.5, because I use this cases array to select the variable, to select the elements of the original array and store the results in this new array here. So this is the array that we will use to make our analysis. And now I, instead of using the histogram function, the hist method of the pandas library, I use the histogram function on Numpy. So I compute an histogram. I call it a numerical histogram because this function will not provide any plot. Just subdivide your data, which are contained in this array here in this case. I provided this array as an argument to the function histogram. I subdivide this data in some channels. They are generally called beings. So I define a number of beings. I say that there are 30 in this case. I put this variable and being in equal to 30, and I provide this variable here as another argument of the histogram function. So I will produce an array which is called mag beings, which it is a two-dimensional array. This is a numerical histogram. It will classify or will subdivide events, seismic events, into beings, into channels, and you count the number of events in the channels. So I run this cell, and then I can separate, I can store magnitude, a number of events, the magnitude of the seismic events, and the number of the seismic event in each channels. I separate this information in two different arrays by selecting the rows of these mag beings two-dimensional arrays. If you want to see the original arrays, just print mag beings. Okay. And you see, you have an arrays over arrays. So it contains the first array here, which contain the number of the events in each channel, and a second type of arrays, which is contain the magnitude. of the seismic events. You can also bring the shape of this arrays. Why it is not this method? Okay, no. Mag being okay. Don't know why. Oh yes, it is not. It is not. It is not a normal array. You see here, it is a tuple because it starts with the um, parentheses, not square brackets. So a tuple has not the attribute shape. Anyway, there are two array stores in the tuple, and the first element of the tuple is an array, and the first element, so the element with index 0, which contains the counting of the event in each channels. And so I will store it in an array which is being mag count. I just will select with this mag big 0, I will select the first line of this array, which is correspond to the counting, and the second line, so this one here, the second element of this tuple is just the element, each element here contains the magnitude of the events. So I have two variables here, which are these two ones that are printed below. Now, I can delete this cell here. No, what I did. I can delete this one. You see that in this array of the counting which count the number of earthquakes in our data set will contain 0. There are some elements which are 0, some channels which are empty. For instance, we have the fourth channel, the 0, 1, 2, 3, the one with index 4, index 3, 0, 1, 2, 3, which correspond to this channel 0, 1, 2, 3, to this channel here. And there are no earthquake having a magnitude which is comprises in this channel with mean value of the magnitude, which is 2.15. So there are other channels which are associated to the 0 element inside in the counting arrays. That could be an issue. That it can be due to the fact that we are using a too large number for beings. For instance, if I change here the number of beings, I put 10 only beings, and I recompute this. I have only 10 channels. I don't have this any zero in these arrays. But anyway, we'll proceed the same by using this number of beings. And we have this 0. Now, these zeros can be an issue because we want to compute the logarithm of the number of events if you want to use the Richter law, which is a law that relates the magnitude of the events to the number of the events, to the logarithm of the number of the events. So we have to take the logarithm of this mag count, being mag count, and this will give some error when I compute this logarithm, base 10 logarithm. So if I run this cell, I get errors because there are zeros in the array. So we have to eliminate this element containing 0, and we'll do that by using this where function. Exactly as we did before, we use already the where function to select cases, to define this cases array. We want to use the where function to select the element in the array which are not 0 in this case. We want the elements of the array which are not 0. And the where function will provide us the indexes of the element which are not 0. So I write this line here, pos equal to np where, so numpy where, as argument to this function. I have to provide a boolean, and the boolean big mag count not equal to 0, this exclamation mark followed by the equal sign means not equal to. So I will get here in pos, and store it in pos, all the position, all the indexes of the element in the bin mag count which are not 0. So I got pos here, and then I use, if you want, you can print it. So if you want to see pos, just look at it. So this is an array. These are all the indexes in this Big Mac count which are not 0. And I use pos to select the actual value. So Big Mac's count pos, square bracket pos, will select all the elements which are not 0 in the array Big Mac count, and also the corresponding elements in the array Big Mac val, which contains the magnitude of the event. So I run this cell, and for instance, I can print Big Mac count here. If I want, I could also print the Big Mac val. Now I can take safely the logarithm of this array because it has no 0 inside. So I can run here the cell, and then I can plot this figure, putting on the x-axis I will put the Big Mac values, the magnitude values, and on the y-axis I put the Big Mac count log values. And these symbols here, it's a string k star, tells to the plot function of matplotlib that I want marker, which are stars, and I want a color which is black. K stands for black in these libraries. So I have this plot here. Now I want to make the fit of this data with linear fit to apply the Richter law, and for this I use the polyfit function, and I use a slightly different version with respect to the function I used yesterday, because now I write here cov equal true. So I want as an output of the function not only the coefficient of the fit, of the linear fit, but I also want the covariance matrix to make some analysis concerning the uncertainty, as Marta asked yesterday, the uncertainty of the coefficient of the fit. So I run fit. You see that now this polyfit returns not only one object, so the coefficient of the fit, but also the covariance matrix. So I write fit, comma, cov. So there are two variables which will store the result from the polyfit function. Now we run the cell. Then I print the type of the variable fit, which is just a Numpy array, and the coefficients themselves, which are this couple here of numbers. This is the coefficient of the higher order term in the polynomial, which is a linear degree 1 polynomial. So this is the coefficient of the term which multiply the magnitude value, which is the independent variable, the x variable. And so if you call mag just the magnitude, that will be a coefficient of the term mag. So you have minus about 1.0809 times the magnitude plus the intercept, which is 4.86. So your line, your regression line, will be minus 1.89 times the magnitude plus 4.86. This is your Richter law, essentially. And then you can print also the covariance matrix, and you can see the uncertainties of the coefficient of the fit. The first column would refer to this coefficient here, the second column to the second coefficient. And there is some correlation between the two, so the covariance matrix is not diagonal, but there is some correlation. If you want to compute the uncertainties, you have to make some work in order to use this covariance matrix to get some realistic uncertainty of each of the variable. Then I want to make a plot of this data, so this actual data here, and at the same time the regression line. So what I did here was I wrote here is just define a number of points of this regression line, 10 point. Then I define an array here by using the NP link space function of Numpy. This function will generate an array of numbers, of floating point numbers, from min mag, so the minimum magnitude that we have in our array, we define it above as a parameter. Where is it? Okay, min mags, okay, min mag here, this is equal to 2, and max mag, which is 3.5. So an array of 10 here, 10, which is written here, 10 floating point number between 2 and 3.5. Then I use the function polyval, which is coupled to polyfit. Polyfit will provide the fit. So our coefficient of the fit are stored in a variable which is called fit. Now I use polyval, and I provide to this function the fit, so this coefficient of the polynomial, and a list of value of the independent variable, and polyval will returns an array of containing the value of our straight line, or our line, computed according to the Richter law. So it provides the value of the fit of the coefficient, and it will apply this polynomial having this fit to our independent variable values stored in this array, and will returns those values which are saved in this mat count plot array. So I run the cell, and now we generate the plot, the PLT figure. Then I start to plotting this line. PLT plot will provide to the plot function, we provide this array of the independent variable. Then the value of the dependent variable computed from the fit, and I will assign a label that will be a linear regression that will be printed inside the frame of the figure. Then in the same plot, I will plot also the actual values, our original values, so bin mag val, the magnitude value, and the count, the logarithm of the count, the real logarithm of the count. I will use stars, black stars, to identify each event. Not each event, but each value here. If you don't write anything, if you write, in this case, I don't write anything here of this type. I could write, for instance, K this way, without putting any symbol here. As here I put a star here, I put nothing. The function plot will use default and will draw a line. So we'll connect all the points to draw a line. Now I see I run the cell, you see what happened. So the line now is black because I wrote K here. That I say I want a black line. If I want a red line, I can write R, I will get a red line. If I do not write anything here, so I use default, even for the color, I get a blue line, that's the default. I can use black line, but I want a line which is a dashed line, for instance. And I get, why step, all right, use a different. Okay, I have a dashed line. I can also try to use another style for the line. So you have many possibilities that you can look at by looking at the documentation provided for Matplotlib. There are many possibilities, choosing colors, style of the lines, and so on, marker type, different value. And you see that to each line or to each data set, I assign a label, linear regression in this case, actual values in this other case for the stars. Then there is a function legend here with a keyword where they frame on equal to false. Now I will show you what it does. And it will print a legend inside your frame. You can also change the position of the legend in the frame by using keyword to this legend function. If you don't use any keyword particular figure for a particular optional value, there are defaults which are used by the legend function that will find the best place to put the legend so that it does not overlap, if possible, with the drawing that you have. So there are smart choice of position for the legend. There is frame on equal to false, which is not the default. The default is frame on is equal to true. So if you don't specify nothing as argument to the legend function, the frame on equal true will be valid. And you see what happened. If I use this one, the legend will be put inside a frame as a frame with some thickness and color for the frame. I don't like this frame around the legend, so I always write frame on equal to false because as a matter of taste, you can of course change this one. Then I put a value for the label here of the x-axis for the magnitude, just PLT x label magnitude. PLY label, PLT y label for log equal to log count for the y-axis. It is written this way. You have many possibilities to change the size of the label here. This one, you can change the color, you can change the way it is written, you can change the style of the title, and so on. By using options which are passed to this function here that are fully documented in the sites, the official sites of Matplotlib that discuss the libraries. Okay, now questions? So here there's an exercise that I will not do here and I will not explain to you, but you have all the possibilities to work on this exercise if you wish. As I told you yesterday, you have to practice to learn really how to do things in Python, and that could be a good exercise for you just to start. You look at your procedure, and you may wish to automatize all the algorithm, all the procedure under a function. So you can put everything inside a function that will take some data, downloaded from, in this case, the NGO site, and arrive to produce figures like this one, to produce a computation of your Richter log, or computation of the fits, the line, fit in this one, just by using a function. Or maybe you can also use classes. You can pack all the functions that you could define to arrive to your final results, and pack all the functions inside the classes. That is maybe a Richter class that can your calculations in one shot. So that could be very, very useful to use to learn to structure an algorithm in classes. Okay, so try to do this exercise, not now, of course, but when you are alone, when you have some free time, try to do this one. And I will load this notebook in the GitHub site so that you can look at it, and you can see the code which is written inside and try to restructure it. Now, I switch to another notebook if there are no questions on this one. And these notebooks makes a different things. Now in the previous notebook we used least squares function, polyfit function of Numpy to make a linear regression, to make some polynomial regression, some data. But in many cases, you don't have a model which can be expressed conveniently in a polynomial form. You have maybe that you have data that can be fitted by some user-defined function, so the function you want, and so you have facilities to do that in Python. So in particular, a library of Python. We'll do that now by using this work by using a function which is called carFit, and this is a function that is under the Scipy optimized library. So this is a very large library of Python, Scipy. This library contains a lot of methods and classes and functions, and under the classes there are the classes that belong to a subclasses which is optimized, so Scipy optimized, and under these Scipy optimized there is a method which is called carFit. It will be useful for us now. So I don't want to import everything from Scipy. I just want to import the carFit method. So I write this statement here. From Scipy optimize, import carFit. That's the syntax that I use. So I will, if I run this cell here, now I just delete all the kernel. So I start from the beginning. So if I run this cell here, now I'm importing in my environment all these libraries. Numpy is NP, matplotlib, pyplot as PLT, pandas. I will use pandas to read, not to read data. In this case, I will use pandas to format tables of data that I want to compute, and we will see how. I import this carFit from Scipy optimize, and also I import this other function partial from a library which is called functool. We will see how it works now. Just an example to do some particular operation. And I also import plot. Plot is not a standard library that you can find in under the package, the Python package, but as a file, as a Python file, which is written in the store in your disk here, plot.py. It must exist in the folder of the notebook. So I import this one. If you want to have a look at this file here, you can open even notebook in Jupyter, and this is the a function. This is a class, in fact, that I wrote for other users in my large project on thermodynamics of minerals. Anyways, it is a class that accepts many arguments and attributes for the method it has, just to make plots by using some defaults that you can change to define the style of your plot and so on. So I will use this plot class for making our plot here. It's very general fits here. So I import it. Then what I want to do now, the analysis will be the analysis of some values of specific heat at constant volume of some minerals. That's the specific heat of pyrope as the temperatures change. So the function is not a function, it's a set of data. It could be experimental data. In this case, they are not experimental data. They come from a calculation from first principles by using quantum mechanics. Anyway, it doesn't matter. I have some values of specific heat of pyrope as a function of temperature, which are saved in a data file here under the folder data file. If I find them, these are for quartz. I don't remember what I saw. CV data here. CV data, so just a simple file containing two columns. The first column is the temperature. The second column is the specific heat in joule or mole Kelvin. So the temperature is in Kelvin, and you have this specific heat up to 700 Kelvin, from 20 to 700 Kelvin. And I will read this file by using log.txt function of Numpy. Then I want to fit a model on this data, which is the Einstein model. So the Einstein function which is generally used to fit data of a specific heat at constant volume in a range of temperature not too low. So generally it's in the high temperature range. There's this model. I don't enter into details of this model. It's just a model that can accept one parameter. A model that this parameter is this EPS. It is an Einstein temperature that can be used to compute the specific heat at any temperature T. Fairly complicated function, got exponential inside that involve this parameter together with the temperature. This is Einstein Fun. This is just a function and contains this one parameter. You can also refine the model by using two Einstein temperatures, so you can a little bit complicate your model. Instead of using just one Einstein temperature, you can use two Einstein temperature. So you have a model that makes use of two characteristic temperature of your for your specific heat, and you are free to choose one function or another function. So the Einstein 2 function containing two parameters to make the fit. So we want to fit our CV data with respect to the temperature. We want to fit, we use for a fit of the Einstein function. So a good way to start to say, all right, we will have our data, we will have our two functions, and maybe it's useful to group these two functions inside a class. So I define a class, Einstein class, that defines these two functions as method of the class. The computation, for the computation, the specific heat also involved the knowledge of the Avogadro number. So it's better to have this Avogadro number inside as an attribute of this class. Involved the use of the Boltzmann constant. So I also stored my Boltzmann constant in the variable KB, which becomes an attribute of the same class. And also, it is required the knowledge of the number of atom for speed formula units inside your substance. Now, for instance, if you want to work on pyrope, you have 20 atoms in the formula units. So this variable APFU will be equal to, in that case, to the number of atoms in the formula units. And this change according to your substance. So while of course the Avogadro number and the Boltzmann constant are always the same for every substance, of course, the number of atoms per formula unit depends by the substance that you are using, that you want to compute. So I put in this init function, this dunder init function, I put the APFU as a argument, so that this will be used to construct the instance of the Einstein class for a given substance, and we'll put this argument APFU to as an attribute of the class. So this is a very simple class. We have also a method that allows you to change these number of atoms per formula units just by setting it with using by set APFU function, and will just store the value that you provide as input to this function, to this method here, to the attribute, assign this value to the attribute of the class. So I run this cell, so I define this class, and then I proceed. Now I read the data from the data file. Also, I will define here in this case an instance of the class plot that I imported by using this import plot, as I told you before, just used for making plots of some type. So I just define an instance of this plot class. And then I define Einstein class. I define an instance of the Einstein class. And I call this instance with the number 20 because I want to work with PyROP. I know that PyROP contains 20 atoms per formula units. So I call this definition here Einstein class with 20. This with 20 will be passed to this argument APFU of the init function and will be assigned to this attribute here, as I told you before. Then I load the data. They are stored in the data file folders, and the file is cvdata.dat. Then I select, this is I use load.txt. So when I finish to execute this function, I will have a two-dimensional arrays because this file contains 2 columns. And I will extract the data from the first column here. The first column is indicated by the number 0 here, the index here, 0 here. And if you recall, this a column put here says to the Python interpreter that you want all the data in the column. So it is a slicing. And so the first column contains the temperature, so I will put all the data in the temperature variable, which is an array. The same for the second column, contains the CV, the specific heat. They will be stored in this variable CV. So I run this cell. Everything is okay, so there are no errors. Now, maybe we will do that you want to limit your data of the CV in a given temperature interval. So I told you that this Einstein model works well. It's reasonable for data which refers to temperature which are not too low. Now, my data that we see in our file for CV start from 20 Kelvin, so they are definitely too low temperature to be used for an Einstein model fit. So probably I will have to limit my data range concerning the temperature in some interval. And so I define a temperature interval. So I define this function data limit that will accept 2 arguments. So there's an optional argument with keywords. So a minimum temperature of 0 as default, and the maximum temperature that is NP max temp. So I put this Tmax as an option to Tmax. Tmax is an optional keyword, and it can be provided or not. In case it is provided, I can provide the value of temperature I want, or I can put some default. So if I don't specify Tmax, the default will be used. In this case, this Tmax is NP max temp. So I will use the Numpy function max to find the maximum temperature in the temp array, and I will set Tmax equal to this maximum temperature. It could be done, it's legal to do things like that, but this is not a good practice. I wrote it to show you what is a good practice could be and what is not a good practice. It's not good to provide default to a function by using a number that can change according to your data set. This number, Tmax, by default, can change for a different data set because a different data set temp will have a different maximum temperature. So this Tmax value will change with with the data set. So it could seem smart to define Tmax equal to the maximum temperature in the data set, but it's not good practice because it can be the origin of bugs and errors. Because you think that the default number provided to a function should be a fixed value, not something that change according to your particular data set. So I put that to show an example bad practice. So, and eventually you can change to a different definition of the default. Then what does this function do? Simply, okay, you define a Tmin and Tmax. Then you select the value of the temperature by using a Boolean in this case. The value of the temperature comprises in these two limits. So temp equal to greater or equal to Tmin, and temperature less or equal to Tmax. So this Boolean we say that will be Boolean array will be saved in the variable select. So will contain all the temperature, all the position in the temperature array for which the temperature is comprised between these two limits. And I use the select, so the list of Boolean, true or false, to select really the value of the temperature and the corresponding value of the CV. And I will store the value in this T list and CV list. So if you work with data limit, at the end you will return to new list for which the value will be comprising this range of the temperature that you use as argument to the data limit function and the CV list. Okay, so this first function will do this work. Now you have this other function, very large, it's not that big function, but anyway, it is what it is. You have this Einstein Fit function that will do all the work. You see that this Einstein Fit function will also provide as an argument the minimum temperature and the maximum temperature. So I will set this minimum temperature and maximum temperature. That will be used in the data limit function. So the first thing that Einstein Fit does is to call data limit in this by providing this value for the temperature. So the data limit will be used by the Einstein Fit function, return value of this T list and CV list that will be saved inside these two arrays, two Numpy arrays here. Take into account that now, when you run this function, these two lists, T list and CV list, will be local variables, because you see there are no global definition, no non-local definition. So these are two local variables that eventually can shadow global variable definings outside the function definition. But there are no variables like this one in the external environment to this function here. So simply we call data limit. Data limit returns two lists, and these two lists will be saved here in our local variable. Then you see there are other many other optional arguments that you can pass to this Einstein Fit function, and I emphasize that they are many for a reason that I will do later. So there's fix equal to 200. We don't know exactly now what fix is. You note that I don't write here. I didn't write any documentation here. Just I didn't have the time. There is this guess. There is the bounds. There are endpoints equal 100. Now we don't have idea of what all these parameters are used for. So what they meaning? I will see. Now this guess equal to 50 is used to create two lists. a guess one list, which is a list containing just one member. So technically, even if this contains just one member, this guess one is not a single variable, it's not a scalar. It is a list. It is a list containing just one element. And also I have this guess two list, which contains guess repeated twice. So this is a list containing the value 50. If I don't change this, I provide the default value for guess to my function. Guess one will contain 50, and this one contains 50, 50. So two equal numbers in the list. Then there is this use of this curve fit. Now, I separate these two. We really do the computation. We really do the fit of our values, CV values, to the function that we define, to the Einstein function. So what is the syntax of this function here? You see that I write this simply curve fit, and there is not any dot notation before. There is not the name of the libraries from which the function curve fits come from, because I use this syntax here in the import in the function. From Scipy optimize import curve fit will allow you to use the function curve fit without specifying the libraries. If I, for instance, wrote import Scipy optimize and stop, I could also use curve fit, but I have to prefix the curve fit name with the name of the library. So I should write scipy.optimize.curve fit, unless I use some alias. Maybe that I could write. I write it as for your reference. I can write import Scipy optimize as maybe as in this way. Can call this one in this way. If I write instead of this one here, I write something like this. Now I have to call curve fit, where it is here, by using the alias. So I should have to write this one. But in the way I work it, I use a different notation, different syntax, so no need to use any alias, no need to specify the number of the name of the libraries before curve fit. Okay. Now, what is the syntax of this function? It accepts the name of a function, the name of your fitting function, and you see that I prefix Einst function, because now this Einstein function belongs to a class, this class here, and I created an instance of the class which is called Ein. So the name of the method is not properly a function, is a method, so a function belonging to a class. The name of the method will be Ein.Einstein fun. So I have to write here Ein.Einstein fun. This is our function here. Then I provide the list of the independent variable, the name of the dependent variable, and also I have to provide, if I want, this is optional, a guess, a reasonable starting point. It's not that easy to make fit by using general function. You can have all sorts of numerical problems. Generally, you have to, it's better to provide to your curve fit function to provide some initial guess to start, the reasonable value. Now, reasonable value for this guess is used to provide an initial values of the Einstein temperature. We want to fit our functions, and we want to refine the the value of the Einstein temperature. You see that our Einstein function accepts a value Tt, which is the temperature, and a parameter. Now, this parameters is the parameters which will be refined. So the syntax of Carl-Fit will recognize as a first argument to the Einstein fun, will recognize the independent variable. Everything that follow the independent variable name will be treated as a parameter to be refined. And this parameter is the Einstein temperature. We want to get the Einstein temperature. So this gas here, this 50, correspond to the Einstein temperature, an initial value of the Einstein temperature. Could be 50, could be 100, 300, doesn't matter too much. But certainly, for instance, putting here a negative value is not a good choice, because of course the Einstein temperature is a temperature and it has a positive value. That probably is not very large, probably is not 10,000 Kelvin, is something which is between zero, not zero, but between maybe 20 and let's say 5,000, but cannot be outside some limits. So I define a number here as a gas which assign it to a default value of 50 that could be reasonable and a good point to start to make our fitting. But this curve fit accept this starting point, this gas, not as a scalar variable, but always as a list. So that's why I put this gas inside the square bracket to define a gas one list. And this gas one list is passed to this parameter P0. P0 is not free, it is not a name that you can choose as you want. P0 is the optional argument to the Carl-Fit function that takes the value of the initial gas. So you put here P0 equal gas 1, and this list will be passed to the parameter P0. So Einstein function here, the function that I want to fit, the value of the independent variable, the value of the dependent variable, and the initial gas. Then I also put here another option, which is bounds equal to bounds. And bounds is a list, is a tuple. You see here, I have a tuple defined as an input argument to the Einstein Fit function. That is 10 to 1,500. What is it? This contains the limit, the numerical limits for the parameter to be refined. So I don't want that the Carl-Fit try to refine my Einstein temperatures if that try to goes outside the limit. I don't want, for instance, that the Einstein function get negative, Einstein temperature get negative. So I constrain the possible value of the Einstein temperature between bounds, 10, 200, 2,500. And so I pass these bounds to the parameter bounds of the Carl-Fit function. So this is the parameter name, and this is the value of the parameters that I assign to the parameters. Bounds equal bounds, not an equation, not an identity, because these two objects are two different things. One is the keyword, one is the value that I assign to the keyword, which happen to be the argument of the function Einstein Fit that I wrote about. So, and there are other parameters which are default parameters that I generally always use, xtol, ftol. These are used to control the precision of the fitting. So I want a very, very strict fitting, and I use this two parameters that control in some way the precision of the accuracy of the fitting. You can delete that if you wish. You can use other values as beginners. If you want to try to use this Einstein Fit function, you can try to see what happens if you change this value here. Not very important now in this notebook. Okay, this card fit will provide you, will make the fit, will try to make the fit. It can fail sometimes according to the nature of the data you input and the nature of the function you input as a model function. You can get errors, so card fit which does not exceed. And in those cases, you can try to work by using different guess initial points, so different guesses. Um, Generally, you can get error if you don't use these bounds here. So maybe that you arrive at the end with not an error, but with Einstein temperature which are unreasonable, maybe some negative values. You don't want them. So you can help the card fit function to go to the end and go to the end by providing you reasonable value by providing these bounds. Very, very useful. In some other case, you just get errors. Anyway, this will be not the case in our with our data. And the card fit returns two arrays. Um, the first one is the arrays containing, I call it Ein Fit1, will contain the Einstein temperature, so will contain the parameter which is being refined, and the second array, Cov1, will contain the covariance matrix. In this case, the uncertainty of our refined temperatures, Einstein temperatures. Then there is also this other call to the card fit, but that will use the second function, the function containing two values for the Einstein temperatures. So a model with two temperature Einstein temperatures. But there is no difference at all with respect to the first call. I simply use a different function. The independent variable is always the same. The dependent variable is always the same. Bounds is applied to both the Einstein temperature that I want to refine. So EPS1 and EPS2. Both must be limit in this range. And the gas I have to provide, I had to provide two values for gas 2 to be assigned to P0. So gas 2 must be a list containing two values, and I use 50-50 because if I run the program with, I run the function with gas equal to 50 as default, then the gas is 50 for both temperature, and I have a list of two element gas 2, which I'll pass to the parameter P0, and so on. Now, this is a spatial possibility, not frequently used. Anyway, maybe that you want to try to make a fit by using the two temperature Einstein function, but you want to try to fix one of the two temperatures. So I want to make a fit with the Einstein 2 function, but the value of the Einstein temperature for one of the two possible values of the Einstein temperature, I want to be fixed to some particular values. Let's say 300 Kelvin. I want to make a fit where EPS2 is equal to 300 Kelvin, and the second temperature could be could have another values, could be refined. We want to refine the variable EPS1 by fixing the value EPS2 to some particular value. So you see that I'm using this fixed parameter here that I used in the list of arguments, the Einstein Fit function. I put this fix equal to 200. Fix to equal to 200 will be passed to this EPS2, which is an argument of the Einstein 2 function. We will see above. Einstein 2 function as a temperature, accept the temperature, and two other parameters. These are generally the parameters that are refined, EPS1 and EPS2. But now what I do here, I use this partial function, which was imported from the func2 library. So from func2s, import partial. What does this partial do? Partial will take is a function, so receiving some argument, enclosed in these parentheses. The first argument is the function on which I want to work. This is the Einstein 2 function. And I say EPS2 equal fix. So I will put EPS2 equal 200 by default in this case. What partial does? Partial will create a new function in which one of the argument, the last one in this case, the EPS2, is been fixed. So this new function, which is fixed fun, I will the value returned by partial, and the value which is a function itself, is stored in this fixed fun. So this fixed fun will be a function that depends only by the temperature, of course, and by the other argument which was not fixed, which is EPS1. And EPS2 will be treated as a fixed parameter, so it will be not refined. It will be not refined by the function CalFit that will work on this fixed fun. T-list, CV-list, independent, dependent variable, the same bounds. P0 equal guess one, just a list of one element, because now we want to refine only EPS1 and not EPS2, because EPS2 is not even a parameter of the function fixed fun, because it's been treated as a fixed parameter inside the function Einstein 2. And I did that by using the partial function. That's more or less clear? I hope so. There are other possibilities to work with in this way to make CalFit, so fitting of function by fixing some parameters. This is a way to do that, but there are other possibilities. There are 3 or 4 different possibilities to do the same thing. This is one that is legal, is particularly simple. Then I make the CalFit, all right. Now, then there are some prints here. The value of the Einstein temperature from the model with one Einstein temperature only. The printing of the parameter from the model having two Einstein temperature refined, and the print of the result from the third fit, which use this partial function, this fixed function. And so you can print the result. Then what I compute here, you should recognize it. I have I create an array by using least comprehension. So I will use the Einstein function with one temperature, one Einstein temperature, the Einstein function with two Einstein temperature, this other function here with one temperature fixed. And I will pass as argument to this Einstein function, I will pass the coefficient of the fit, so the Einstein temperature. You see I started this list of coefficient, could be 1 or could be 2, anyway it can be a variable number or a coefficient. And I will compute so the CV from the model now by using the Einstein temperature that was refined. And for a number of temperature which are comprised in this T-list, and T-list is defined at the beginning, and here. So I will compute the CV values from the model, not as they are no longer the value of CV retrieved from the data file. So model 1 will contain the CV value computed at the same temperature contained in T-list from the Einstein function here with one Einstein temperature. This model 2 will contain the value of the CV computed with the Einstein function with two Einstein temperature. And the third model, so the model 3, will contain the temperature from this partial function defined here. So EPS2 has been fixed to fix, and you have also the refined temperature here. Okay. Then let's go on. This is a very long function. Then I makes a series here, a series by putting together all these lists I create, all this array I create. So I create a list of lists or a list of arrays. The first array is just the temperature list. Then you have the CV list. These are the specific heat from the data file. These are the specific heat from the model 1. Round 2 says I want just 2 decimal points for my numbers of the CV. The model 2, same thing, I approximate with 2 decimal number my CV, say same for model 3. Then I build a data frame. I build a data frame by using the pandas data frame function, pandas data frame method, that will accept this area that I define above as a list. I accept a list, and I provide index to this list. So the first element will be the temperature, then you have the CV experimental, then the CV from the 3 model. I transpose my frame, and I will print, so I will change index with columns. I will exchange row with columns, in fact. So I transpose this just for purposes of printing, and I will print the result by using the print to string function that can be used also to print a table on a file. Anyway, I will use print to print the table on the monitor. Then there is the plot. We'll discuss the plot in a minute. Now just run this one here. And I call this Einstein Fit Function by providing a value of the temperature, the minimum value of the temperature equal to 20, not to 10. And I also provide a value for fixed variable here for the model 3 equal to 400. Now I run this, and you see what we have here. We see up to the plot. Now I just look at this number here. So we have temperature model, one temperature model, 633 Kelvin. This is printed by the message here, the instruction here. Then we have the second print, temperature model, 2 temperature models. These are the Einstein temperature refined. And this is the fixed model, for which one of the temperature was fixed to 400, and the second was refined. So this is the refined value. You have a list. This is the effect of this print df to string index false with the backslash n at the end. Just create a new line for every line here. And you have a table with the temperature value, the value of the specific heat experimental, let's call the experimental specific heat, so the specific heat retrieved from the file, the original one. Then you see the model 1 results, not too bad, but not too good. You have discrepancies which can be very large, especially at low temperature. For instance, here we have a prediction at 92 Kelvin. You have a prediction of the specific heat, which is 24 joule over mole over Kelvin, instead of 85. And discrepancy reduced at larger temperature. But anyway, for instance, 700 Kelvin, you have the discrepancy, which is more than 10. This is about 14 joule over mole over Kelvin, higher than the specific heat, the experimental specific heat. The model 2 works much better. There are discrepancies at low temperature, but generally it works much better. You see, for instance, at the close to the room temperature, they are almost equal, the value you retrieve. And even high temperature, the discrepancy is not that high, so just 2 points of difference between these two ones. The model 3 is in between the two models, the model 1 and the model 2. So not 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 too bad, let's say, not too bad. Then probably want to evaluate better the quality of the fit by making plots. So in this case, I will use the plot function that I imported for my function for my file plot.py. So I compute the Einstein by the Einstein function models. I will compute the CV in a range of values, and I define an array of t-plots of temperature from Tmin to Tmax in a number of points. So a number of points, endpoints here, is an argument of the function Einstein Fit, as I set to 100 here. And so I will get an array here of, this plot, of 100th number of temperature in the range Tmin, Tmax. Then now I compute by using list comprehension as done before. I will compute the CV according to the tree model by using the three different functions for IT values in this t-plot here. Then I create a list. This is done for the use of the plot function that I define in my files. I created an instance of the class by using the variable myplot. So this myplot is an instance of the class plot, which I imported at the beginning. And this variable, this method that I use, will accept, in the case I use the method multi, will accept list of a value of the independent variable and of the dependent variable to be plotted at the same time in our graphical frame. So I create list x and y of the temperature, and so this t list is the list of the temperatures for the experimental data, and these are the list, the three lists of the temperature for the computed functions here. So correspond to CV1 plots, CV2 plots, and CV3 plots. I have the corresponding temperature. Then I have the list of the dependent variables, so the list of the specific heat, experimental and computed. Then a list of the style that for which I want to plot my curves. K star will indicate marks, black marks for the experimental values. Then dashed line, continuous line, and dash and dot line. Then a list of labels that I want to write in my data frame in order to identify the different figures. Then I want to set some parameter for making the plot. So I will use LaTeX font. I will use size for the labels that are 60 points. So some other parameters, and the DPI equal to 200 because I want to have a relatively high resolution figures. Then I run the method multi. Will take all these argument, so the list of the independent variable, the list of dependent variables, the list of the styles, the list of the labels. I want to write my x-axis label in LaTeX, so T with K as a temperature in Kelvin. And the CV, I not want to write C underscore V, but I just want to write C with V in the LaTeX style, with this unit of measure. I want a figure with this dimension, and I want to save it on the file, save true. So all these arguments are arguments to the multi function. And so the result was this one. So you have your actual values in stars, your stars. You see the LaTeX style for printing your labels here. You have CV with CV written in this position here. You have, anyway, looking at the important thing, you have these methods this different function. You see that the black lines corresponded to these 2p fit, so the fit made by the Einstein function with 2 Einstein temperature. This dashed line is the other function with just 1 Einstein temperatures. It doesn't perform very well. It performs by chance well in this region here at about 200 Kelvin. But at high temperature, we have an overestimation, the CV, and a big underestimation, low temperature. This other curve here is the third model with 1 fixed temperature, and the other which is refined. Then I can run this other function here, Einstein Fit T min max. So I will select the data from the CV from 300 Kelvin to the maximum temperature. And you see what I get here. It's much better fit, but especially concerning the 2 model to the two temperature fit. This one is very, very accurate. Also, the Einstein fit with 1 temperature fixed doesn't perform bad. So this other curve is pass to our data, but the one model, the model with one temperature only is not very good. So you have this line which still have problems. So generally, by using an Einstein function with just one value of the Einstein temperature is not a good idea. If you want to reproduce data, you see what is the magnitude of the error that you can get. Even if you work at high temperature, even if you work in the region where the Einstein model should work. So Marta, can you tell this to Rosangel, because I know he's using some of this model to predict specific heat for some minerals. That the model with just one Einstein temperature generally is not very good. You should work with at least a model with containing 2 temperatures, at least, and also at most. I also try to make some computation by using models for seeing 3 Einstein temperatures. They diverge. They don't provide a good result at all. The best to do is use a model to fit. So this is quite accurate.
If he doesn't listen to you, I don't think he will listen to me.
Okay, so you have this table. You also
Sorry, can I ask something? Can we see, for example, some indicators, numeric indicators, the quality of the fit, like the chi-square or something?
Yeah. In fact, they are saved in this in variable inside the function. I just didn't print that. I have this Cov. This is the covariance matrix, so you can compute the uncertainty of this fit, the uncertainty of the refined variable. But unfortunately now, it could be very easy to print this out, but in the implementation of this function, I forgot to print this out. I could add now on the fly this value. But I say unfortunately because as all this has been done inside the function, and all these variables are local function, if I can try to print this value when the function finish, but of course they no longer exist in our environment because they are local variables. So when the function exit, all this value will be destroyed, and so I will have any longer this value. I have to print them inside the functions themselves to see those values. So you can do that. You can add columns here. You can compute manually, for instance, manually or by using some structure here in this function, the difference between the CV compute and the experimental CV, and so you can provide columns that contain these delta values for model 1, model 2, model 3, You can make some average of the discrepancy that you obtained as a summary statistics at the end of the column. So you can do whatever you want, provided you write the appropriate structure inside your function here. Now, this notebook showed you several things. One thing is just to make how to make the fit of data to function or to function to some data. That could be the main point of this notebook, how to use the function car fit. But I think there's another point which is much more informative for beginners that want to learn how to write programs to make computation. I wrote this function here having in mind a beginner that starts to write some programs. And so I wrote in a style that could mimic the way a beginner will work. And it is full of bad practice strategies. Bad practice. Okay, at the beginning I was already smart to define my Einstein class to put inside the Einstein functions. But there is one point which I don't like very much, is the fact that in this function here, this class here, that should be a place to store only functions, I put an attribute to this class, which is the number of atom per formula unit, which is relevant, which is a number that will change according to the data that you provide to your functions. It should not be logically, it should not be stored inside an Einstein class that provide just the functions. So I should rethink a strategy for which this attribute is somewhere else, in some other class, and so in some other instance of the class. Not here, not good. But that's not too bad after all here. So I have this class, Einstein class, and could be acceptable. Then I have this operation here that maybe that could be done inside some other function. Okay, but not too bad here. The real point is this sixth function, Einstein Fit. I emphasize at the beginning that I have a lot of argument here of this function. There are too many arguments, definitely. And one argument, for instance, is not very elegant because it is the default which is assigned as a function of the data set that you have. Not good having as default like this one. Then I have other parameters here that I don't know what they are unless I go through the code and see where they are used. Of course, I can write some documentation here and to explain, I should add some documentation that explain the meaning of all these parameters. But if I want to see in the function where they are used, in what way, I'm forced to go through the function to read, to find where they are used and in what way they are used. So too many parameters that are not so intuitive, and they don't talk about themselves. That's the point. They refer to very different things. There are too many, and they refer to many different things. This fix is a parameter that is used for building these fixed partial functions. So it is used here in this specific place. So it has to do this fix with a particular model. Then guess is a parameter that is used to provide some initial guess to your models. Then there are these bounds that are also used for the car fit execution. Then you have these points equal to 100. the hell means points? Well, points is used to make the plot, to compute some list of temperature values for which we have to make the plot. Very bad here, because mix this list of argument mix together too many things relating to too many different function this function want to do. So define an interval to the temperature for making the fit, define parameter for making the fits, define a parameter for making for construct a particular model, and define parameter for making a plot. Not good. Another thing which is not good is the fact that this Einstein Fit Function does too many things together. Philosophy of the program of information technology people is that a function should do one thing only, not many things. One can say, all right, this function does one thing only. It just does the fit and plot the result of the fit of our Einstein model of the specific heat with temperature. Well, that's not one thing. You see that to this function will call another function to limit the data in a particular temperature range, does the fit, compute the value of the CV from the model, prepares a series of data to be printed in a table, compute the parameter for making plots, and execute plots through the function myplot. So there are at least 4 different things that this function does. So how to do? This is not a good function, not well-written function. A much better way to work is to restructure all this script, all this program in a way that is much more structured and much more close to the good practice of programming in Python, in any language, not only in Python, of course. So I have this other notebook here that works in a different way, which is much more readable. Does the same things, but does not exactly do the same thing that the other notebook did, because can do something more. I add new facility, new features that that was not present in the other case, and all the objects I create are much more structured. So I will show you now in the last half hours, in this 30 minutes we still have, to see what I wrote here. And what is the structure that you should use for making a program like this one? So think about that. One of the most important thing is not at this level of for this course is not to learn how to use some wonderful function, special function that are defined in the libraries of the Python. For instance, this car feat is very useful function, but okay, I show you an example, but it is not the point of this course. Imagine that you are in a laboratory, and the laboratory acquired a new instruments, and the first day of the instrument is being installed, there is some guy from the place where you purchase your instrument that will show you how all the performance of the instrument, what the instrument can do. You show you wonderful things. You press this button, you get this number, you can this type of measure, look at the accuracy of the measure we did, look at the uncertainty of the variable we measured, and so on, so on. And you see this very wonderful instrument in your lab, but you don't have idea of how to prepare the sample to go to the instrument. You don't have any idea how to elaborate the results of the instrument in some particular workflow. You got in the lab with a sample, and you put the sample under your instrument, you make some measurements. But you well know that to get the sample is not, generally is the tricky part. It's not simple. You have to prepare your sample in order to make the measurement. So you have to know how the wonderful instrument works, but you have also to know, you better know, much better, how to prepare your sample in order to go to the instrument. And you also have to know how to use the result from the instrument, some workflow, to produce your manuscript and to publish it. So here is the same. You have very particular, very good functions from Scipy, from this Carl Fit, for instance, but there are many, many others. But you have to know how to use this function inside the workflow, inside the program that make use of this function. And this program, this course, was mainly dedicated to this point, learning how to prepare data, how to deal with the data, to deal with the basic Python features, to prepare the programs that complete a workflow. Otherwise, I could say, all right, we have. Imagine that I did this course in another way. I start to talk to you about this wonderful function called fit and many others. All right, you see, oh, how good, fun. Python has this feature. You can make curve fitting. You can do minimizing function. You can find the solution of equation and so on, so on. But then you will not use that because you don't know how to use that. You don't know how to arrive to the use to prepare data for these functions. So and one point of the course is to learn how to prepare programs that work with data and to use those functions. And you have to prepare them in a structured way, not just as I did before in the previous notebook. I wrote a function that do everything in one shot, because that function is not readable. If you write the function, it works indeed. You'll try to use it. You got results. Then you put in the drawer those function. Will not use it any longer for, let's say, 6 months or or even less. Then after maybe 6 months, you go away. You go to your computer. Your boss asks you, "Well, right, make the fit of the specific heat of quartz, for instance." All right, I already wrote my function, and I will try to do that. You go to your computer, you will load your code, you will look at it, and you say, "My God, what is it doing here? How does this function work? Why I'm getting error here?" So a lot of things that will make you lose time, a lot of time, because you have to study again your function to see step by step what it's doing. Now, if the code is written in a different way, to structure in a different way, it could be much easier for you to go back to look at it or study it. It will be much easier, and it will be much easier to be used by yourself or by other peoples, and it will be much easier to implement new algorithm inside it, to modify it, to add some new features. Otherwise, it's a mess. It is a mess, really a mess. So now, this is just an introduction. I don't want to scare you, but the point is that one. You learn to structure your programs in some way by using as much as function you can, and by using classes. Classes is the secret. So the structure by using classes, the best you can do with a program, with a language like this one. So I redefine a class, Einstein classes, the same as before, but you see that I just put in my class, still there is the attribute APFU, atom per formula unit, but I have just set it to 1 at the beginning. Then will be the work of other functions, other classes, to set correctly this value. So because this value is used in the function, Einstein Fun or Einstein 2 Fun, I am forced to provide the default value for this parameter. So I wrote just one, but this value must be upgraded by other function of your system, and we will do. So essentially, the Einstein class is the same as before. Then you have this new data class, this data class, that does a lot of things, a lot of attributes, and a lot of initial attributes that are set up at the beginning. But you have only three arguments that you use at this constructor. As I told you, this done the init function is a constructor of the class. Apart from the keyword self, that will be substituted with the name of the instance of the class, you have name, file name, APFU. What they are. Name will be simple, the name of the phase you are working on. For instance, if you have PyROP, you can choose, for instance, PyROP as a name, or PY, or what you want to identify your phase. Then a file name, the place where the data has to be found, and APFU. So the number of item formula unit will be an input number of this class. Then there are a lot of other attributes which have been set to initial value, which are just empty arrays or number which are just zero. In some other case, you have other numbers, but in general, you have all these attributes set to initial value, which is something like that. They are not strictly necessary. I could also write a init method here that does not provide any value, initial value for this other variable x or each, y or each, x, y, min x, so they could be absent from this list. But it's a good practice to put some initial values, even if they are empty, in this init function, just to see what your class is going to handle. So there will be attributes that will contain the numbers and lists here, as soon as the data will be loaded. So it is a good practice to know how many and what are the attributes which are relevant to your class. Then you have to read the data class. Will work with class. You know that if the class is called data class, you will know that this is a class, and this will work with data. You have to handle data. So you don't have difficulties in understanding what this data class could do. It has to handle data. And this data should be read, so from some place in your disk. So why not to define a function, which is a method of the class, which is simple, called read self, and then path. You have to provide a path to read the data. So this data will be read from file which in some folder. This folder has a name that could be also default. So you see that I have an attribute here as I put the self path equal to dot between string. This is the local folder. This is the folder where the Jupyter notebook or this class will be saved. So if you don't specify nothing for path here when you call the method read, the default will be used, and the default is just this one, this dot here, the local folder. Otherwise, if you provide another path, then it will be used instead of this dot. So you can provide path something else, something another name for another folder. Then you will construct a file name by using the name that you provided at the beginning, this file name that you provide at the beginning as for your system, for your data. And so it is written the file name as a local variable now in this read, which is constructed by adding the path / to file name. So you will have at the end of this structure, you will have a file name which contain the name of the file path comprises. Then you will load your data, load txt file name. This will be stored in the data local variable. This is a two-dimensional array, and from this dimensional array, two-dimensional array, you will extract the two columns. One is the temperature, and you will save it in these X origin arrays, which has a self in front of it. So this is an attribute that will be stored in this attribute here. So you will have permanently saved. And you see that I will work with temperature and CV and specific heat, so why not call these X and Y T and CV? Well, I did not do that because maybe that I want to use this data class for other programs too that does not deal with specific heat and temperature, can deal with something else. So your variable X and Y will assume a different meaning, but you can recycle this class to treat other cases for other quantities which are not temperature and specific heat. So you have this anonymous name X and Y. Generally, you study at the high school and even the university, the X is the independent variable and Y is the dependent variable. So that's a good way to name your variables here, not by using temperature or CV, but just using X and Y. So you can recycle your class in some other occasion. Then you can find the minimum of the independent variable and the maximum by using the Numpy minimum and maximum. You store this in these other two attributes, so they are permanently saved. You can compute the sites and store the sites of your data set in this self-num. And then you can create copy of your data set in another variable, another attribute, X and Y, because maybe that you will use function that changes for instance, we saw that we can select temperature in a given data range, which is different, this range from the original range read from the file. So you have to you could modify your temperature range, but you want to preserve the original data range. So your original data range was saved in the X origin, Y origin. You create another array, a copy, by using np copy, and you save this in this other attribute X and Y. Then also you can provide a flag which is false, that tells if will indicate if a selection of the data was done or not. But we will see. Then we have this select function. You see that before in the original notebook, I provide a function that will select data in a given range. Well, that function becomes a method of your data class. This method select will have some tmin and tmax equal to 0. I can write tmax equal to 0. No, it's better here, equal to 0 here. So the default for tmin is not indicated. There is an indicated default for tmax, which is equal to 0. That's strange. It seems an unreasonable choice because tmax can be equal to 0. Is a maximum value of the temperature, so y equal to 0. Because this is used to see if you are choosing a default value for tmax or not. So if tmax equal to 0, so if I don't indicate nothing when I will call the method select, I have to provide a tminimum, but I can, for instance, I have the possibility to not indicate a tmax. In this case, tmax will be equal to 0, but the select function, the first thing it does is looking at this tmax and evaluate this boolean. If tmax equal to 0, so the default, then tmax will be equal to self max xx. And where is this max xs? Max xs was defined by the read data, method, and was put to the value, the maximum value of the temperature, in this case, that we found in our data set. So this contained the maximum value of the temperature found in the data set. And so if you use the default, where is it here? If you use the default, Tmax will be equal to the maximum temperature. It's not zero. It's just the maximum temperature. Then you select. So this is the name of the method. This is the name of an array, of a list. This is a Boolean list, which is computed in the same things that the same way that we done before the original data file by using those particular function, that particular function. So we select all the temperatures and CV having temperature in the interval Tmin Tmax. And okay, then I set fit flag equal to false false here. You will see later why. Okay, now I will compute the minimum value of the temperature, the maximum value. I will save it in these two variables here, because now the minimum and maximum temperature have been changed by the function select. And so I can say that the selection has been done. So I will set the flag selection flag equal to true to say to the system that, all right, I selected a limited range of the temperature, so that the program will know it. There's a selection has been done. You are no longer working with the original data, but with the selected range. Then a good idea to write an info method that will print out all the features of your data. So this print will print the dataset name, the name of the file, the number of formula units, the number of points. If you made a selection, if self-selection flag is true, then print original temperature range restricted to this range and to this interval. There is a point here that I never told you before. When you have a line like this one, that should be one line only. This is a statement print, and you have open your parentheses here, and you close here. This is an instruction which is very long, and will go on too much on the right of your monitor or your files if you are editing in the files. So you can go to a next line, and you indicate to the interpreter that this thing which is written here is the continuation of the preceding line. You put a backslash here, absolutely nothing the backslash, and you go on the next line, and the interpreter will understand this correctly. So you say, this is a unique print instruction that will print everything according to what is written here. So this print will print information concerning your interval in temperature that you selected, but it will only print it if you really did a selection. Otherwise, if the selection flag is false, nothing will be printed. Okay, then you print the maximum temperature of the original data set. Then, if you made the fit, one temperature Einstein temperature fit or the other fit with two temperature fit, in that case, the flag will be set to true. Now they are false at the beginning. You didn't still make any fit. So in this case, these two variables will be this or this one will be false. If they are false, the result of this Boolean is also false because there is an OR, but an OR, remember that this is an OR. This fit is, this variable is false, this variable is false, false or false is false, not false or false will be true. So if not, this is true, if this Boolean here is true, then will be print, there will be this print. Fitting model, no. Will still not have done any fitting. Else, if this is if not this expression here is false, then print this one. So if self-fit flag 0 is true, then print one temperature model. If this is um, this other flag is 1, this other flag is 2, it will be print 2 temperature model and the parameters, the fit parameter. So you see now explain last 5 minutes and then we'll go to lunch. You see the use of this, what will be the use, the probable use that I foresee for this flag, which is a list of 2 values, 2 Boolean values. If I make, for instance, a fit from by using just the one parameter Einstein function, just one, I will set this value here to true, and the other will remain false. So when the info function, the info method will arrive here, you will find that the first element in this flag, this list, is true, and the other is false. So it will print out only this message here. So it will say one temperature model Einstein temperature, and will print out the Einstein temperature. If I do only the second fit, so the fit with 2 Einstein temperatures, and not the first, then this flag will be false true, and then it will be printed only the second line here. Print 2 temperatures model, Einstein temperature, and so on, the 2 value of the Einstein temperatures. If I did both fit, then all these 2 flag will be true, and then I will have 2 printing. The first one will provide you the temperature, the Einstein temperature for the model 1, and the second print will provide you the 2 temperatures for the model 2. So I did not foresee here the special, the particular case of the partial function, which I fixed one temperature and I free the other one. If you want, you can try to implement also this model in your class here. Then just this thing, so it's apparently a redundant function. This is a Dunder method you never see before. You never saw it before. This Dunder method is a magic method of the classes. I implemented it in the exact way I implement print. I just add an end here at your end because these, right, don't enter in this detail. This is useful for the print function, the print basic function of Python. If I will define, for instance, I will define an instance of the data class with some name. For instance, I can define an instance Python py of this data frame. If I write print py, print pyrop instead, then I will interrogate this class, and the Python interpreter will look for a Dunder function which is called rep, and will print all what is written here. So I can get information by my data set by calling explicitly the info function, or by writing print the name of my instance of the class. And that's all for this morning. Of course, if you have questions, this afternoon I will start again on this data class, and then you see I use it. I restructure the Einstein Fit Function. Now you see that your Einstein Fit Function will accept only one argument or 2 arguments, just the name of the instance of the data class, so the name of the phase I want to work on, and the model 1, model 2, one temperature Einstein function, 2 temperatures. Then we makes all this calculation. So I have this function here. Then I have a function for making the plot. I have a function for comparing fits, and so on, so on. Then you use, when you have defined all these different functions, you make all your computation just by launching the function compare fit, and you see what happens. Okay, so questions? So if there are no questions, well, we'll see you in a couple of hours. Goodbye.
Bye, see you
Bye.
later.
Thank you, bye.
Bye. Thank you.